Okay guys, I'd like to introduce you to Rob Mueller. Rob is a senior technologist at our Surface Systems office, and he's going to discuss a little bit today about Razor.
Good afternoon, everybody. Thanks for coming to Kennedy Space Center. I want to point something out over here. This is a landing pad, and you can see it's seen some action. So when these rocket engines interact with the surface, then they need a landing pad. And so this is an excavation robot, and it's very small because it's designed to go on a precursor mission. You send the robots up on a precursor mission, and they prepare the site, and they gather the regolith. And they gather the regolith because the resources are in the regolith. And so with several of these small machines which go to the moon or Mars on a small lander, we can actually do remote operations before the astronauts get there and prepare the way for the astronauts. So this is a mining robot. It's designed to mine regolith and extract the resources from the regolith. And it's also a new way of digging because the reaction force is very low on the moon and on Mars because of the reduced gravity. When you have no reaction force, you need to come up with new ways of digging. So this is a digging machine like you've never seen before because it uses bucket drums with small scoops, and they counter-rotate. So, AJ, can you have a little demo? I'm going to show you how. You would need a big machine like you see on a construction site, like a Caterpillar, a big yellow machine. That's what you would need to get the reaction force. But because the drums' forces are counteracting each other, it can dig. So another feature of this machine is currently robots, for example, the robots on Mars, they can get stuck. They can easily get stuck in soft soils. So what we've done is we've designed this machine, and if it ever did get stuck, normally it drives on these treads here. If it gets stuck, it lifts itself up on the drums, and then it simply drives out on the drums. So this is a very robust machine. It's designed to tolerate failure. And then once it's outside of the trench that it's dug, then it can start digging again. And the whole point is to get to the water ice. And the water ice is thought to be about 1 meter below the surface. So if we can dig a trench that's 1 meter below the surface, we can access the water ice, and water is the key to life in outer space. So that's what this machine is designed to do. So it's a robot that we send out ahead of the astronauts, and it goes and gathers the resources, specifically water ice. Any questions, please?
What did you say its mission duration was?
This is just a prototype, our first generation prototype, and we're building the second generation now. Our plan is to have a robot that can last 5 years in outer space.
So plans for a larger one?
It's a scalable design, but because we're limited by the size of the lander, that's what constrains the size right now. So we built this for a Phoenix class mission lander, which is about the same as the lander that landed on the Phoenix mission on the moon. And right now landers are very small, so we have to build small machines. When we get bigger landers, we can build bigger machines. But that's the whole point of this, is to keep it small. If we need more excavation capability, we'll send several of these, and they'll operate in a swarm. Yes?
Can you give us an idea of the cost of one of these and how much that would be different as opposed to a real life version of the flight either the moon or Mars?
Okay, good question. We worked on this, a team of about 5 people for 2 years. That's a ballpark of the cost. I can't give you an exact number, but you can do the math. And so it's relatively inexpensive because it doesn't have all the flight qualified components on it. But then as you get closer to flight, you use better components, more expensive components, and the price will increase. I would say it's going to be several million, but not in the single digits million, not more than that. It's going to be cost effective primarily because it's so small. And also, as you know, the technologies are constantly advancing, and with Moore's Law, and we're getting better technology every day.
In terms of the swarms, can you give us a rough supposed to be? I mean, what's it be in systems?
Yeah, to create 10 tons of oxygen on the moon for returning. So you make the oxygen, and each return journey uses about 4 tons of liquid oxygen. So if you had 2 return flights per year, and then you had 2 tons